talking about buckling instabilities of filaments in viscous media.
Hello. Hello, good morning. And thank you to the organizers for the invitation. My name is Alejandro Monastra. I am from the University of General Sarmiento. It's a relatively new university, 20 years old. It's at the north of the city of Buenos Aires in Argentina. So me and Florencia Carusela, my collaborators, we are both working in this university. Luciana Bruno, she's from the University of Buenos Aires, Department of Physics. And then Veronica D'Angelo, she's also from University of Buenos Aires, but from the engineering faculty. So, I will talk about buckling instabilities of filaments. This is a work in progress now. And so it was motivated first about microtubules in the cytoplasm of living cells. So I show you some video about, these are experiments on living cells. This is a frog cell. So the microtubules are identified with some proteins, that fluorescent proteins. We can see the microtubules that are like the bones, the structure of the living cells. And what we observe is that these filaments, semiflexible filaments, they undulate, they have some wave motions that are produced like buckling. As if you take some bar that is some semiflexible, you compress it, then you will have some deformations. And so if you look these videos in these structures of the cells in more detail, so for example, you see a horizontal microtubule there, and then you observe there a kind of buckling, an undulation. These are, it's not well understood yet the origins of these bucklings. It could be, of course, the cytoplasm inside the cell is a very viscous media, but then you have a lot of organelles and stuff inside the cell that can be pushing and constraining the microtubules, so that's the origin of those motions. So in order, we have done already work specifically on microtubules, and so they were interested also to modulate this with a macroscopic system. So this is a kind of plateau, plenty of glycerol, a very viscous liquid. And so this is a mylar filament, like the filaments, that you can push it. It's very thin, and so it's semi-flexible, and then if you push it, you observe these undulations. This will be a macroscopic model of the microtubules of a cell. So we want to study how these instabilities are produced in these semi-flexible filaments. Yeah, I mean, I will go in the wave equation, in a mathematical model. And in general, they are not solitons. They are like modes of the hydrodynamic wave equation. I think I have half an hour, no, for my talk. Well, I don't know. Yeah, I have more time. So then that's where the examples, but of course this can be applied to, these are the microtubules are inside the cells. You can have external cilia and flagella of cells. This can describe also some foldings of polymers change and some deformations of flexible fibers. Maybe, I don't know, if you have hairs in a flow, they can also flex each other due to the flow, to the motion of the liquid. So I will present a mechanical model of the a flexible, a semi-flexible beam. You have a beam in this configuration. So small l is the coordinate along the beam. It goes from 0 to big L, that is the length of the filament. And each element of the filament will have a position R of L, describing its configuration. And so we have two types of energies for a semi-flexible beam. We have an elastic energy. I call it elastic. It's coming from the strain or the compression of the filament. So it's just directly related with the deformation of the filament in the longitudinal direction. And then we have a bending energy coming from the flexion of the filament that is proportional to the square of the curvature of the filament. So it's all in terms of the Young modulus E of the material. We are supposing always an homogeneous filament. The area and the shape of the filament, transversal shape of the filament is always the same. And it's related with the transversal area and the moment of inertia of the section. Sometimes the product Young modulus times moments of inertia, E times I, is called the flexural rigidity. So it gives us how difficult it is to flex some beam. So we can compute from these potential energies the force per unit length. So for some small element of the filament, which force it suffers from the neighboring elements. For the elastic energy, we have an expression. The bending energy is really a difficult and long expression. It depends even up to fourth derivative in the position. Yeah. Of course, we think this filament inside a viscous media, so we have a viscous force that is opposite to the velocity of the element. And the general case of a filament, we have a drag coefficient that is different in the longitudinal direction along the tube and along the filament and in the perpendicular direction, but they are all both of the same order of magnitude. So sometimes we will simplify them to just one drag coefficient. We put all these forces in a Newton equation. So of course it's the acceleration times the mass. But we are thinking in an overdamped regime where we neglect the inertia terms. So we put this equation, the sum of forces equals to 0. We can do some mathematics doing to solve this equation, full equation is impossible, but we can do a small deflection approximation. So the configuration of the beam is just a perturbation of a straight shape. And of course, the perturbations along different from this straight shape will be much smaller than the total length of the filament. So putting this into the equations, the x and y coordinates decoupled, and for the y component, that is the transversal deformation along the filament, we arrive to this fourth order differential equation. Although it looks complicated, it's a linear differential equation. And so because it's linear, we can propose an exponential solution in the position L and in the time t. So this gamma coefficient would be a kind of rate that would tell us if gamma is positive, we will have a growing solution in time. If we have a negative gamma, we will have a decreasing solution in time. And we just do some dimension. We take out dimension. We have dimensionless parameters. P is of course, and the filament can be compressed with some force P. And this compressive law appears in the differential equation. So we can solve this with this proposed solution. We can find the modes. And what we can compute is the decaying rates gamma as a function of P. So as as stronger is the force P, we have coefficients gamma that goes, for example, if P is small enough, we have all solutions that have negative gamma. So any deformation of the beam will relax to a straight shape. But as soon as the force P is bigger than a critical value, there will be a mode that will be growing on time. So if we compress with a force stronger than this value, we will have a buckling event. That is what we observed in the experiments. Yeah. Yeah, of course. I mean, it's the same value. This 4p squared in dimensionless terms is compared to the critical Euler force. This is the normal buckling stability of columns, of beams. The question is that when we are... Of course not. I mean, the stability will be there. The viscous medium, what we do is to give a characteristic time of the evolution of the buckling process. So indeed, this gamma scales directly with the viscosity of the medium. So a double viscosity of the medium will have a double growing time. Yeah, in this small deflection linear response. So I plot here the black lines are symmetric modes, and the red ones are antisymmetric modes. So we have these solutions, and I will show now how do look the shape of these solutions. So I have to remark here, this is not an evolution in time. In this video, I plot the shape of these eigenmodes as a function of the parameter P, that is the compressive load. So if I have a low compressive load, this shape looks like a ground state. But if parameter P increases, we start to see the mode. This is still the ground mode of the system, but because the force is stronger, it compresses and we have more nodes of the shape. And so at some there are some range of parameters that the mode looks like it doesn't change, but then when the force starts to grow again, we will observe again another we see here another. So even if this is the ground mode of the system, we have already 4 nodes in the mode. So this is comparable with the shapes that we observe in the experiments. And just that was the symmetric mode. This is the antisymmetric mode. We observe a similar behavior for some forces. And of course, after some value of the parameter P, these are growing modes in time. This is the shapes, and the amplitude will grow in time. Okay. So of course, when we have bigger amplitudes, it was always the small deflection amplitude approximation. When we have bigger amplitudes, and when the force, of course, is not constant, so we have a dynamical situation that the only way to describe it is by a numerical simulation. So we have to discretize the filament in n segments, or we can think about the position of n beads along the filament. So we discretize the potential and bending energy, and deriving these potential energies with respect to the position of each bead along the filament, we have equations of motion with the viscous force. We have to add, of course, the boundary conditions and some constraint that could be, if we want to study some external force, we have to add it to the model. So we were studying the the experiments on glycerol with these filaments. So these filaments have more or less 30 centimeters long. They are very thick, the thickness is very small, and the Young modulus is around 2 gigapascals, and we can compute all the dynamical parameters of the model. The coefficient for the drag per unit length, this should be estimated experimentally, because one should solve the Navier-Stokes equation, and it's not simple in this case, so we obtain it experimentally, or we estimate it experimentally. For the experimental condition, we also study the clamped solution condition, boundary condition, so that the derivative of the filament in the tips is 0. In the experiment, we have one right end is fixed, and the other one, it moves with a constant velocity. So because the velocity is constant, the force will be varying force. Some numerical questions about the algorithm. Of course, the stability will depend on the election of we integrate the equations of motion. It's a first degree equation in time. So, but of course, if we want to reproduce a very curved shape of the filament, we need a lot of points n. But this will also, we should go with the delta t time, we have to go to a very short time. There are one can estimate analytically some time scales. The elastic time, that is the time that the perturbation is transmitted along the filament. It would be like with the sound velocity. It's related with the sound velocity. And also we have another time scale regarding the relaxation of a shape. If I start with any configuration, the form configuration, I leave along the filament, this will have characteristic time, a long characteristic time to relax to the straight shape. So for our cases that we studied, we need a very short time step. And of course, if we increased the number of segments n, we will obtain better and better solutions. Around 500, the solutions converge. Anyway, for the up to 150, we obtain a quite reasonable solution with small error. So, for example, we plotted here the amplitude of the buckling as a function of time, and we observed that for different number of n, up to a time of 10, we didn't have any significant difference, although for longer times we have some differences, but for our purpose in the first stage of the work to study qualitatively, it was okay for us. So here are one of the experiments in glycerol. This is with a very slow velocity. We observe here the tip slowly going on. So at the very beginning of the event, we see that the wavelength is shorter, and then it accommodates and it becomes a longer wavelength. Yeah. Yeah, of course. Only, yeah. In the limit of very slow speed, you will have only one bump. But that was at constant force. If I do it really slow, I'm doing with a force always very near to the critical force. And in that case, also the solution is just one bump. So this is the experiment, and we simulated here with the parameters I gave already. So we observe qualitatively a very similar behavior. I think if I stop at the beginning, yeah. I mean, I have to start, yeah. Yeah, at constant velocity. Yeah. Of course, the initial shape in the numerical simulation, I have to have some small deflection from the straight line, because if not, I have just only a isostatic compression. I mean, it's like the instability, but even some thermal noise will deflect the straight line from. Yeah. Yeah, we observe at the beginning that there are the stabilities originate here, but we have also deflection on the other side, on the other tip of the filament, because there are a kind of a transmission that is elastic up to the end, and then, but if I will show now with a higher velocity, and we will see a different behavior. So it's like we have some different waves, and at some point, for example, this goes up. We have just one or just few bumps at the very end. So this is experiment, a very fast experiment. And of course, we have the perturbation. Even if the perturbation, the biggest perturbation is in this end, you can observe at the very beginning in the other tip that there is also a perturbation. And we did the simulation. I mean, it looks slower, but it's, because of there are many pictures on there, but this is 50 times faster than the previous simulation. So, but we observe also this this big perturbation in one end. And at the end, there is even a crossover in the shape. And I mean, in the experiments, we do the compression, and then we wait and we observe a relaxation of the system. So, and this is the relaxation of the previous simulation. So here the tip is, we stopped the tip, but because it was a highly curved configuration, with time we observe it relax. But for example, the other simulation, it was just a fraction of a second, this compression. And this takes a minute, almost a minute, to have this relaxation. This is related with this relaxation time for bending, that it was around 260 seconds, of the order of minutes. So, we studied up to now mostly qualitatively the process, but we can know from these eigenmodes at constant force is this buckling process at constant velocity. At the very beginning, if we have an almost straight filament, when we compress it, the compressing force grows and grows to a very high value. So we are in a force that is several times bigger than the critical force. So that's why we observed that the growing deformation have a very short wavelength. And then, because the compression load grows, we have well, I already said that, and we have short wavelength mode develop. But as soon as the buckling start to grow, the compression force, the compressive force diminishes, and so we have this deformation that have a longer wavelength. So the conclusions and perspective for this work is that, well, we observe qualitatively, we have a reasonable understanding of the situation. Higher compressive velocities imply stronger compressive loads and more instabilities. The constant force buckling is well understood in terms of these eigenmodes. The numerical simulations have a good agreement with experiments. So what we have to do now is to do better and more precise measurements of the experimental system. I mean, the velocities are well estimated, but we are doing a tracking software to have the shape of the filaments in the experiment and to compare with the simulations. So that's all. Thanks to the organizers again, and thank you for your attention.